Welcome to Physical Attacks and Countermeasures, the eighth session. We talk about correlation power analysis, or CPA. This is the slide of or last slide of the previous session, what you have seen. We have seen the DPA means that you can categorize the side channel leakages into two groups based on the guess that you make for the key, right? You guess the key, and then based on the guess that you do, you select one intermediate value, and based on that intermediate value, then you make a binary decision. Some part of the side channel leakages go to one group, another one to another group, and then you check whether these groups are different from each other or not. And then, for example, with a t-test, you say which key candidate is the most probable one. You know? What we discussed that, okay, why we should have a binary decision. Now we want to categorize the leakages into more than two groups. And what are the options? And we discuss, and we said, okay, one thing that we can do, we use a correlation. Yeah? But for that, we need to model the power consumption. It means that we need a model, or let's say a hypothetical model, to estimate the amount of the power consumption of the circuit or leakage of the circuit, and then correlate these hypothetical power consumption values with the real power values that we measured from the device, and again identify the most probable key candidate. Yeah? And this, the result of the hypothetical power model, should be also dependent on the key. You know? Means that you guess the key again, you select one intermediate value, and based on the intermediate value and the leakage model, you report one particular value for the hypothetical power consumption. No? We will see this. But the main important part is how to model or predict the amount of power consumption. It can be done in different level of abstractions, and then depending on the amount of information which are available to the attacker. Some of models or hypothetical power models can be used by the attacker. Some of them can be used only by the designer. Yeah? You may say, some information, for example, the netlist of the circuit, how it's built and so on, they are not necessarily known to the attacker. If you go to the market and buy a device, usually you don't know the, for example, the netlist of the circuit or details of the implementation. Yeah? Then you need to select a different abstraction level to be able to predict or estimate the amount of power consumption. These level of abstractions can be set as analog level. Yeah? Means that you, for example, know exact implementation details. For example, you are the designer, you know exactly how you build it in a hardware case. And even you know how the transistors actually behave, and you need actually the transistor netlist, the transistor level netlist of the implementation, including all parasitic elements and so on. Because you studied computer science, you may not have seen this or learned this, but there are definitely some simulators or analog simulators, commercial one and also open source ones. If you have heard about HSPICE or SPICE, you build a circuit based on transistors, based on resistors and capacitors and everything else, and then you can simulate the circuit at every point in time with very high accuracy. The simulator may give you or tell you how much current, for example, is passing through the circuit, the exact amount of the current. And this is based on usually solving some differential equations. For that reason, it's super slow. It takes very, very long time to simulate, for example, one AESS box. If you just have one AESS box and you want to simulate it at the transistor level. And then, of course, it depends on the time steps. Means that with which accuracy, temporal accuracy, you want to have the result. You want to have the value of the current passing through the circuit. If, for example, go for the picosecond, 1 picosecond, it's different if you select, for example, 1 nanosecond. So I can tell you, depending again on the machine that you use and the size of the circuit and the information that you have about the parasitic elements and so on, 1 very high accurate simulation of AES box in the transistor level may take a couple of minutes, just for one input that you give to the AES box, just for one input transition. But it can cover everything. Yeah, it can include all the glitches and the shape of them and everything. And it's done usually by the designers, not by the attacker, because the attacker usually doesn't have that information or doesn't have access to that information. If we go a bit higher in the abstraction level, we reach the logical level, means that you still have the netlist of the circuit, but netlist of the cells. How the cells are connected, how the gates, AND gate, OR gate, XOR gate, flip-flops, registers, how they are connected together. And you may also have the delay of them. How much is the propagation delay? If the input is, for example, one AND gate is 0, 0, and the input changes to 1, 1. Now, how long does it take till the output of the AND gate changes from 0 to 1? This information, if you have, and also delay of the gates, and also some back annotated information. If there are capacitors and resistors in the circuit, you can also model them, and they affect on the rise and fall time of every gate. And then you may get the shape of all the glitches which happen to the circuit. If you remember, we talked about the glitches. And then by this, if you have all this information, you may say, okay, I can capture exact the glitches which are happening in the circuit. I mean, it might be still erroneous, but it still has a good quality or accuracy. And this model is actually called toggle count model, means that when you have the glitches, then you count the number of toggles which happen in the circuit. And if we remember, we talk about the dynamic power consumption, and it actually comes from the changes which happen at the output of the gate. And then by counting the number of toggles which happen inside the entire circuit, then you have an estimation about how much power is consumed. What is important for the hypothetical power consumption, you don't need exact value of the current or power or anything else. No, you just need something to be proportional to the amount of current or power. Similar to the power consumption traces that we measured, if you remember, we usually have the result of the A to D directly, which is, for example, signed integer value, 8-bit value, but you don't convert them to voltage or current or anything else. Then if you count a number of toggles, then you may have again a good estimation about the amount of power consumption. What is also important to consider is that this model might be used by the attacker, but usually you also need that much information about the netlist of the cells, and this might be not available to the attacker. And then this might be still used by the evaluators, or let's say the designer of the circuit. Then, but the good thing is, I mean, comparing the logical level with the analog level, it's much faster than the analog level. For the analog level, it takes very long time and it's very high, very accurate. But in the logical level, you decrease the accuracy, but you are much faster than the analog level. In the behavioral level, which is the highest abstraction level in this domain, it's just about description and some guess about the amount of power consumption. And this doesn't need any information about the implementation usually, and this is what the attackers try to do. It means that you just guess how much power is used, higher or lower, and so on. And this is what we already discussed. The most common power models for the attacker, or from the attacker's point of view. Then we have the Hamming weight model, just the number of ones in a binary representation of the data. And we discuss about this. Why? Because of the buses and the microprocessors, or the values which are processed by the combinational circuits. And also the Hamming distance model, the number of bits which are different in two consecutive process data. And then by this, we, as I discussed previous session as well, that Actually, we look at the numbers which are different in a register for two consecutive values. But the registers themselves do not consume that much energy that we take them as the source of the power consumption, but they supply a combinational circuit. And then by more changes at the input of the combinational circuit, which are coming from the register, then you have more power consumption. And also toggle count model is also used for the attackers, but if you have the information about the net list of the target device, this is also possible. Then we need to also review the concept behind the correlation. One way to deal with the correlation or correlation coefficient is the Pearson correlation coefficient, which measures the linear dependency between two random variables. You should keep in your mind that this is only about linear dependency. This linear dependency is super important. I mean, it's not any dependency between two random variables, just the linear dependency. If you have two random variables, if one of them goes up, the other one goes also roughly up. If another one goes down, the other one also goes down, and so on, somehow. Means that there are different ways and different statistical tools to measure the dependency between two random variables, but not necessarily linear. And then correlation coefficient is only able to tell something about the linear dependency between two random variables, not between any other dependency. And how do you estimate this? Is the covariance of x and y. This covariance you already learned before. We discussed about this expected value of mean free x multiplied by the mean free y. Mean free means that we remove the mean from x and we remove also the mean from y, and then is divided by standard deviation by x and standard deviation of y. And actually this is normalized. The correlation coefficient is actually nothing than normalized covariance. And in the discrete domain, what we do here is the covariance, the expected value. There's the sigma of 1 to n if we have n elements for every of these random variables, or let's say the samples we have from these random variables, xi minus the mu of x and yi minus mu of y. And mu of y we already know. I mean, because we are in the discrete domain, we get the average to estimate the mean. And here, this should be actually the variance, but you need to divide it by n, and here divided by n as well, and here divided by n. For that reason, they are actually cancelled. Because 1 over n here, and 1 over n, and a square root, and then they are cancelled. Or you can actually calculate the covariance, which is 1 divided by n, and then calculate also here the standard deviation, and then this should be normalized. And what is important, the correlation coefficient is always between -1 and 1. And if you write a program later and then check when the correlation value is above 1 or below -1, then something is definitely wrong. Good. And then what we do in CPA or correlation power analysis, one of them, x, is, for example, the power consumption values, and y is the hypothetical power values. And again, similar to DPA, in the CPA, the attacks are performed of every sample point independently. Means that every sample point you consider, and then this x, for example, is power values, and they are all power consumption of one particular sample, and y is the result of the hypothetical power value. And what is also nice, and it becomes easier to calculate, you need to perform this attack that you will see, compute this correlation coefficient for every key candidate, means that y will be dependent on only the key candidate, and x will be dependent on the sample point. And then here, you have to repeat this over all sample point, and you have to repeat this over all key guesses. How do we use correlation for power analysis? We need a leakage model. This is the reason that I explained different hypothetical power models. And then with this leakage model, we observe or predict how the intermediate values actually affect the power consumption. And as I said already, Hamming weight usually for microprocessors and Hamming distance usually for hardware implementations. And if the leakage model and also the assumed design architecture are correct, then power values are highly correlated with the result of the leakage model. You mean this hypothetical leakage model? And of course, assuming that you have the correct intermediate values or guess the intermediate values correctly. The process or the algorithm is very simple to DPA. You guess first the key byte if you consider the AES. Yeah, I mean, this is simple, and the key is 8 bits, 0 to 255, but you guess the key. For example, you start from 0, and then for all power traces that you have, n, then you compute the result of the S-box as an example, similar to DPA, result of the S-box. And then you apply the leakage model, like the Hamming weight model, for example, over the S-box output. And then you have here hypothetical values. How many of them? N, because you have n power consumption traces that you collected. And of course, for each of them, you have one plaintext, or plaintext byte. And HV is a vector of hypothetical values. And now what you do, you correlate this vector with the power consumption values at only one time instance. Again, you get a vector of one time instance of the power consumption traces. And then what you do, you correlate the result of this hypothetical power consumption with this vector, which have the same size. Yeah, of course, when you want to estimate the correlation, the size of the vectors should be the same. And then what you do, you repeat this correlation for every sample point independently. If you have, for example, 1,000 sample points, then 1,000 times you repeat this correlation by keeping the hypothetical power consumption vector fixed, and by changing this to all sample points. If you have 10,000 sample points, then you have 10,000 result of the correlation for only that key candidate that you guessed. Now, and then you repeat this for all possible key candidates, then you have 256 times 10,000 result of the correlation. Then you have a big matrix of the result of the correlation, and then you can plot them and see whether you see something or not. And if everything is fine, the highest correlation in absolute value, you have to take the absolute value because you don't know how the power consumption is actually proportional to the hypothetical power consumption that you have selected. If you remember, we had one example that in some points of the power traces, they are inversely proportional to the Hamming weight. Somewhere else, they are directly proportional. Then because you cannot guess at which point in time you are and what is the relation, then you don't care about the sign of the correlation here. Because I actually need to review something for you with respect to correlation. For example, you estimated the correlation between X and Y. The result is actually the same. Correlation between X plus A and Y plus B. Actually, the result of correlation will be exactly the same. It doesn't matter you bring one of them up, you bring the another one down, doesn't matter. And if you also scale one of them and say correlation of X multiplied by C and Y multiplied by D, this is correct if C is larger than 0 and D is also larger than 0. It doesn't matter if you scale them and you shift them, everything will be the same as long as the C and D are not negative. Otherwise, if one of them is negative, then what happens then? The sign of the correlation will be different. For example, this will be the minus of correlation of X multiplied by C and Y multiplied by D if C is smaller than 0 and D is larger than 0. Of course, 0 should be completely excluded. Yeah, if one of them is negative, then it changes the sign of the correlation. You can also write some program and check this by yourself and confirm this easily. Before seeing one example, I would like to show you two other slides. Here is taken from the DPA book again. It's a visual representation of what happens in CPA. If you look at here, plain text or ciphertext, we consider plain text at the moment, but if you remember, I explained for the DPA, you can also select the ciphertexts, but attack the last round of the encryption. And here, for example, is data, and this is the key. And the size of the data is large D, here in this representation. And the size of the key hypothesis is the large K or capital K. And then the hypothetical intermediate values, for example, the AES box output, all possible plain text and all possible key hypotheses. Then you have a matrix of size of D by K. And then you give it to the power model, for example, the Hamming weight model. And then you get this hypothetical power consumption matrix, which has also the size of D by K. And then you have the measured power traces, which has definitely the size of D. The number of rows is D, but the number of columns is not necessarily related to the key candidates. I mean, this is T, for example. Again, you have, suppose that the large T is 10,000, means that you have 10,000 sample points in every of your power traces. And then the statistical analysis here is the correlation, means that you take this vector, you correlate it with the first vector here. I mean, the first column with the first column, and then first column with the second column, first column with the last column. And then you build actually here one row of here. And then second column with the first column, the second column with the second column, second column with the third column, second columm with the last column, and so on. And then you have at the end matrix of the correlation with the size of the K and the size of the T, K by T, which is the number of key candidates and the number of sample points that you have. And then you can plot this and check whether you see something. Another representation, which is similar to what I showed you during the last session for the DPA, is that you have this part of the circuit, plain text XOR key, and then a box, and then one plain text byte you consider. This is a vector, long vector of the plain text bytes. And then these are the power consumption traces. And then, as I explained, you select only one time instance of them. And this is the vector, the same size of the power values, real power values at this sample point, only at this sample point. And then you start with guessing the key and say key is 0. And then the box output is C9 till here 27. Based on the plaintext that you have, means that 12 XOR 0, 0, and S box. And then you give it to the hypothetical power model, for example, the Hamming weight model. If you remember for the DPA, for example, it was the LSB, 1 bit. And here, the hypothetical power model. And then what you do, you continue this with other key candidates. Again, plaintext 12 XOR 0, 1, and then S box. And the same for everything till you get all vectors of the hypothetical power consumption values. And then you easily correlate this vector, which is fixed, with the other vector, which is a hypothetical. Real power values with the hypothetical power values with the same size for this key candidate. And then you get only a single value here. By this correlation, you get a single value here. But the other correlation, correlating this vector with the second hypothetical power value vector, you get the second value till 255 for the key candidate, or FF. And again, if everything is fine, means that this point in time is relevant to these processes and is also relevant to the hypothetical power consumption model that you have, means that the Hamming weight and the number of measurements are enough, because what you are doing with the Pearson correlation coefficient, we are estimating again the correlation. And then we should have enough number of samples to estimate the correlation with enough accuracy. Then if everything is fine, then one of this is actually much higher than the others and you can recognize it. Or you have to repeat this for all sample points individually and then plot all of them and see how this works. Now we see the examples. Here I have a traces that we have seen together last session, which was a software implementation. Again, I plot one of the traces. This, if you remember, that was the traces or one of the traces. And then what we selected something between 30,000 to 40,000 as the area that the leakage was. But of course, after seeing the SNR, we could select some other parts. Now, and we performed the CPA instead of the DPA. Here, I use all 400 traces, the sample points from 30,000 to 40,000. I target the first key byte, and now here, the model is actually what you see here is selecting the plain text and then give it, XOR it with the key byte and then give it to the SPOX and then afterwards to the Hamming weight model. And then instead of doing any t-test, now I have the correlation, from the start point to the end point. Here, hypothetical value. This is exactly the same vector that we have seen together, which is the result of the Hamming weight model of the SPOX output based on the key guess. Now it's correlated to the traces, all traces, from 1 to 400, and at this sample point. And as I explained, you have to correlate every column or one hypothetical vector for every column of the traces individually. And for that reason, we have to go through a for loop. And the correlation coefficient, or core-coef, which is an embedded function in MATLAB, works only based on a vector. You cannot correlate one matrix to another matrix or one vector with a matrix. Then you have to repeat this. And the embedded correlation coefficient of MATLAB also gives you a 2 by 2 matrix as the output. And the result, what you are looking for, is diagonal, means that there's 1, 1, and 2. I mean, you can check it by yourself. But this is the result of correlation that we are looking for. And then I save this in this matrix, the core, which is at the start 0, 256 cases for the key, and all sample points that we have. If I run this, then it takes some time. Here it is the result. And you can see clearly that one of the key candidates, it's much higher than the others. This blue one, you can also zoom in. And then there is no doubt that actually this is the correct key candidate. What is important is that you don't actually need to have a Hamming weight model. I mean, any model you can use. For example, the DPA that we have seen, which was based on a binary decision, means that 2 values only, 0 or 1. And you can use exactly the same thing with the correlation as well. And then if you have a binary decision, it doesn't mean that you have to use the DPA. No, you can use also the CPA. This is the same attack. And look at here the hypothetical value. This is now the bit get. It gets 1 bit, the target bit, which is defined here at the top 1, which is again LSB. And then the rest is the correlation. I don't do any t-test here, but I can do exactly the same correlation. And the result of the attack is also already there. I can plot it for you, and then you can see this gives you roughly the same result. But look at the correlation. 0.8 is the correlation which is close to actually 1 to the maximum. And usually it doesn't happen. It means that if you have a leaky device, very, very leaky device with very low number of traces, because 400 traces are not many, then still you get a correlation close to 0.8, means that the device has a very high leakage and it's very highly correlated to the hypothetical power model that we have. This was about the software implementation. Now, if we look at the hardware implementation, exactly the same implementation that we have seen last week. Here again, I have the traces, and I can again plot one trace to show you which should be similar. With that one that we have used last session. And now what I do here is exactly the same as what you have seen, Hamming weight model. I have 10,000 traces, and each trace has 5,000 sample points, and I target the attacked key byte 5, as you have seen before again. And the hypothetical power model is also the same, Hamming weight of the Spock's output, and this is exactly the same attack as we have seen together. And if I run this, the result is this. Yeah. You see, it's not really distinguishable. You may think that this yellow orange one is the correct one. Yeah. But if you remember, we discussed that this is a hardware implementation, and the best model should be the changes which happen in the register. If you again remember, the DPA that we have done in this implementation was between two consecutive values, a Spock's number 1, a Spock's number 5, coming from or showing up at the Spock's input or showing at the mixed columns input, and this should lead to higher leakage. And if I perform the attack now using the Hamming distance model, again, I guess that I know the first key byte. Otherwise, I have to search in the space of 2 to the 16. Now, you see here in the hypothetical power model, I have the XOR between two SPOCs. I mean, two SPOCs are calculated, and I get the XOR between them, and I give them to the Hamming weight model. Now, this means that the Hamming distance between two SPOCs outputs, and the rest is the correlation as you have seen. And again, 10,000 traces, each one 5 sample points. And if I run this, the result is this guy, which is very different to what you have seen, based on the Hamming weight model. And you see here is the blue one now, and this is the same key byte actually. Both of them are targeting the 5th key byte. And if you remember that the other one with the Hamming weight model was actually not the correct key candidate showing up. Yeah, and this tells you that definitely for this implementation, it's better to use the Hamming distance model or the bit changes which happen in the circuit. Again, we can also do the attack based on the bit model, but this is again 5th key byte without considering the changes in the register. And if I run this, which I already have done, we can plot the result. And you see, actually the correct key candidate is showing up. I mean, the blue one is the correct one because it's the same keyboard that we are guessing, but it's very different to the Hamming distance model. We can also run the same, similar to what we have done for the DPA, based on just 1 bit difference between 2 consecutive SPOCs, and do the CPA instead of a DPA, but the result will be roughly similar to what you have seen. But of course, Hamming distance model is not possible in the DPA, but now in the CPA, you have seen how much different it was compared to the bit model and also to the Hamming weight model. If you consider the bit model, you don't have any benefit doing the correlation. If you have a binary decision, means that you want to select some intermediate value or something, any binary decision, then I would go for the DPA using the t-test because it's a statistical test and there are some formalities. If the value of the t is higher than the threshold, then I'm sure that everything is actually fine. But if the model is not binary, for example, it's a Hamming weight model, no? Then you cannot use the statistical test just like the t-test. No? This is the point. And as I said, correlation only examines the linear dependency. It means that if the power consumption values depend on the Hamming weight, but they do not depend linearly on Hamming weight, then the correlation coefficient does not help you. Not only this, what we will see later, similar to the t-test, if you remember, we had to, I explained that the t-test only examines these two distributions based on the mean. If the means are the same, but the variances are different, the t-test will not tell you anything because it examines only these two distributions based on the mean, and in correlation is roughly the same. Because you get the covariance. And you also then afterwards you normalize them based on the standard deviation. Means that if you categorize the traces based on the Hamming weight model, for example, you say for the Hamming weight equals 0, the real power values. Yeah? For the real power values, if you get a distribution over one sample point, I mean, if I have, again, a lot of power traces, and I look at only one sample point, and at this sample point, I look at a distribution for the Hamming weight. For example, they are something like this. For the Hamming weight equals 1, it's somehow like this, means that the means are different. For example, again, for Hamming weight equals 8, this is also something like this. You know, means that they are not the same. You know, they have different means. Then everything should be fine. Yeah, I mean, the correlation will help you. But if it's not the case, yeah, if I have the distributions like this, that the mean are actually the same, but the variances, for example, are different. Again, correlation doesn't tell you anything. Yeah, because it just checks the linear dependency. We will deal with that later. You know, how we can, which kind of the statistical tools should we use to be able to still exploit this leakage. One question is, which intermediate value should we take? We just consider the Spock's output. You know, you remember about the DPA, we discussed why we select the Spock's output, because there we couldn't actually use the Spock's input, you know, because only one key bit had an effect. And one thing that we have to consider first is that the intermediate value that we take should be a still in a small size that we can guess. For example, the key of 2 bytes is still doable. I mean, if you have access to a good PC with a high number of CPUs and RAM, you may go higher than the 16, 2 to the 16, for example, 2 to the 32 is also possible either by CPU or some CPU clusters, or if you have access to GPU, you can easily search in the space of 2 to the 32. It's already done by several researchers. Of course, for the attack to be successful, the number of traces should be high enough. This is what I already discussed, because we estimate the correlation by, for example, Pearson correlation coefficient. And then one more thing is that the traces should be very well aligned. This is also what I discussed with you with the DPA. It means that we assume that the clock cycles are very well aligned together. The clock doesn't have a jitter. If it has a jitter, everything will be misaligned. And then if the traces are misaligned, it doesn't mean that you cannot perform the attack, and you have very much noise into your traces, and then very high number of traces are required to perform the attack. Or what you can do, you can align them first and then perform the attack. Yeah, I mean, then you have to consider one reference trace, and all other traces should be first aligned clock cycle by clock cycle and then perform that. The intermediate value should have a high nonlinear relation with the key hypothesis. This is something that we want to discuss now. What we have selected AES Spock's output. If you remember, Spock's is a nonlinear function, and then the relation between the key bits, which are XORed with the plaintext, or let's say the input of the Spock's and the output of the Spock's, is very nonlinear. And why should it be actually nonlinear? What happens if I, for example, consider the Hamming weight of the Spock's input? I can also select the Hamming weight of the Spock's input. The same problem that we discussed with the DPA does not happen, that only one bit of the key has an effect on that binary decision. Now all bits of the key have effect on the Hamming weight of the Spock's input. To show you what can be the result, a simulation is done. This is taken also from the DPA book. You can do the simulation, means that you don't perform the attack actually on real data or real traces. Just imagine that you build the real power consumption also by the Hamming weight model. And not only many sample points to have, you have only one sample point, and the result of the power consumption traces are exactly the Hamming weight model. And if you do this and select the Spock's output as the hypothetical power model, and one key guess is actually here. I mean, this was the key. For example, what I'm saying that we suppose that the Hamming weight of the plain text X or K, and also the Hamming weight of the S box of plain text X or K. Yeah. For this, we perform the attack. We actually generated traces based on this model. It means that both of them, the hypothetical power traces and the real power traces, are coming from this model, and the other one is for the Spock's input. Yeah? And then if you do this, of course, using the Spock's output, you see this key. I mean, the key, for example, is, I don't remember, but it should be roughly 200 something, and this key. Yeah, and in one of them, you know the key exactly because you generate the real power traces. And in another one, you guess the key and you correlate. In the other one, if you are careful enough, you see actually the highest one is also the correct key candidate. It means that with the Hamming weight model of the Spock's input, you still can recover the correct secret. Yeah, but you have a lot of other key candidates that they also show the dependency. Yeah, and we call them ghost peak. We call them ghost peak. Yeah, why ghost peak? Because they are there. There are some peaks there in the correlation, but they do not belong to the correct key guess. And why is like that? If you careful enough, you see that the difference between them is probably only 1 bit. 1 bit difference between them. And if 1 bit of the key is wrong, the result of this Hamming weight will be 1 value lower or higher, just 1 single value. And then if you remember again, correlation was estimating the linear dependency. Then the other one, the odd one of the random variables is a smaller, but a bit smaller. Yeah, means that they follow each other based on the correct key candidate. If the key candidate is not correct, but is 1 bit different to the real or correct key candidate, then still the result of this hypothetical power model is very similar to that one which the key is correct, but a little bit difference. Yeah, and then you see a lot of ghost peaks here. One more thing which is important, what we discussed, we should always look at the absolute value of the correlation, and then you see that the negative one, I mean, is also reaching -1. Means that the key is exactly the inverse or invert of the real key. Which what it does, it changes the polarity, and it will be the exact negative of the correlation. Means that this guy is actually the same if you correlate them. Yeah, this will be the 8 minus Hamming weight of P X or K X or FF. Yeah, if we consider this as a hexadecimal representation. It means that if you invert key, yeah, the result will be 8 minus something. And then if you remember, this is the offset, doesn't have any effect on the correlation, and this is minus, yeah, then one of the factors is now negative, then the result of correlation will be minus, yeah, negative. Now let's see the examples, the software one. This is the attack using the Hamming weight model based on the Spock's output. I have here the same for the attack using the Spock's input. Yeah? If you see at the hypothetical value or hypothetical vector, then just the bit XOR between the plaintext and the key, and then directly to the Hamming weight. And if you run the attack, the result is something like this. You don't have any option actually here. Yeah, I mean, either 400 traces are not enough to distinguish the key, or nothing is absolutely visible here. Then selecting a valid and suitable intermediate value plays an important role in the success of the attack. In some implementations, you have to use, for example, the Hamming weight model of some linear operations like the key XOR. depending on the implementation, depending on what you want to guess. For example, if you extend the attack in the second round, then you have to guess a lot of other things. Sometimes it's okay, or you have to use the key XOR result. But in this implementation, for example, it doesn't help because probably 400 traces are not enough. Now, what are the typical power models? Just as a review, bit model, what I already discussed and explained to you. This only makes the assumption that the power consumption is different when processing 0 or 1. I mean, if you get an intermediate bit or a bit value. And it's very general. I mean, you don't need to have a hypothetical power model like the Hamming weight, because when the CPA was introduced, of course, the power consumption traces of many devices were fitting to the Hamming weight, but it's not like this anymore. I mean, you may still do it to perform the attack using the Hamming weight on modern devices, but not necessarily. No, I mean, you may use or try the Hamming weight and the attack may work, but there is no guarantee that, for example, the Hamming weight or Hamming distance will work on for example, microprocessors. I would say, I mean, personally, I would say Hamming distance model works the best way, because it exactly looks at how many bits are changing at the input of the combinational circuit, either in the processors or the hardware designs, because you can also use the Hamming distance model when you are dealing with the software implementations. When two consecutive values are stored in a register or in the same memory cell, it's exactly the same leakage, and you can use also the same power model. But the bit model is very simple, and then you do not need to have any assumption about power consumption model. You just say, if the bit is 0 or 1, the power consumptions are different. I mean, how they are different, I don't care, they are just different. The Hamming model and Hamming distance model we already discussed a couple of times. What we did not consider, and I also explained this during the last session, you can have another binary decision, like the zero value model. The zero value model is also a pretty well-known model that you can select or do the attack based on DPA or CPA, because it's, again, binary decision. And it tells you that, select a model in a way that if the input is, for example, 0, then the result of the power consumption is also 0. For example, you say zero value of x is 0 if x is 0 and is 1 in all other cases. Where does it come from, the zero value power model? And when you implement mainly the AESS box, do you remember again what was the AESS box? What is the definition of the AESS box? That was inversion first in the Galois field. For example, you say S of x was the x inverse, and it goes to an affine transformation. And what is the meaning of x inverse? X multiplied by x inverse, the result should be 1. Now, in the Galois field, using a particular polynomial, and with one exception. The exception is 0. When x is 0, x inverse is also 0, but it doesn't fit to that equation. And for that reason, mainly, when the input of the circuit is 0 for the AESS box, usually, the amount of power consumption is usually lower compared to the other cases, because a lot of zeros happening inside the circuit, a lot of zeroing. And then, but it's an intuition, not necessarily. But you may use a zero value power model, and then the result of the correlation will be inversely proportional to this model. It means that if the input of the S box is 0, then the power consumption is higher compared to the others. Nobody can say that, without having access to the netlist and details of the implementation. But this binary decision will also help you to perform the attack, because there are some countermeasures that we will see later, and they are able to protect, for example, the S box when x is not 0. When X is 0, they are not able to protect. And then by that, for example, zero value power model, you are able to perform the attack on that protected implementation as well. You have seen the DPA and a statistical test, and there was a formality that you can easily say, when the t value is over the threshold 4.5, if I have enough samples, then I can confidently say that there is a relation, and a key candidate I can distinguish. But how about the correlation? What is the threshold for correlation? To say if the value of the correlation coefficient is higher than something, then I can select this key candidate and say, okay, I'm pretty confident that this is the correct key candidate. Unfortunately, such a threshold does not exist generally for correlation, but there are some rule of thumbs. Means that if you select the correlation for the correct key candidate, keep it in your mind, correct key candidate, not every correlation. When you have a successful attack, and the P belongs to the correct key candidate at the correct sample point, then you can say that the number of traces is roughly 28 by the square of the correlation. And we will see now in our examples, and we can calculate this together. Means that by this, you can find actually how many measurements you need to perform the attack successfully. The good thing is in correlation, it's usually like this. If you remember again DPA, and if you run the DPA by increasing the number of samples, the value of the t increases if you use more traces. If you plot the result of the DPA for the t-test, for example, this is number of traces, and this is t value. Then this is, for example, again the threshold, 4.5. Then the correct key candidate actually is something like this, and all the others are somewhere here. In the correlation, it's not like this. If you plot the correlation over, again, number of traces, and this is correlation, this is over the number of traces, and for example, the best sample point in time similar to the DPA, this was DPA. And here is CPA. The correct key candidate, the correlation for the current key candidate, you have a lot of things here, and one of them is getting somehow like this, and all the others are going below one thing. This is the thing. Means that for the CPA, the correct key candidate or correlation for the correct key candidate stays roughly the same if you increase the number of measurements, and all others go down. Means that this distance becomes higher. In the DPA, this distance becomes higher. Means that the value of the t increases by increasing the number of measurements. In the correlation, the value of the correlation for the correct key candidate stays as it is, and all the others are going down. And this rule of thumb, this actually finds, for example, here, and says this is n. At the point that afterwards the correlation for the other key candidates go down, and they keep a distance to the correct one. For that reason, you need the value of the correlation for the key candidate. Means that if even you use many more traces and you are here, still the value of the correlation is the same. A value of the correlation at this point and at this point, they are the same. It doesn't matter if you use more traces. Once it becomes successful, it stays successful. Yeah? So there might be some noise and then some other key candidates coming up and down, but this is the trend. By this, you can say that, okay, if I have a successful attack, how many traces I need? But in the t-test DPA, we were looking actually for the threshold to say, okay, the number of traces that we have are enough. Yeah, then we can say this is the correct one or not. Then you can actually turn this into rho is what? Is the square root of 28 by n, easily. Yeah? Means that if you use those many traces here, those many traces, then you can calculate the p and say if the p is higher than this value, if the p is higher than this, by a square root of 28 by n, then you know, okay, this is actually is above the threshold. It means that this threshold, this line, you know, this line you can draw independent of the attack. Because it's just 28, a square root of 28 by n. And then if the correlation comes over this threshold, then you can say, ah, this is probably the correct one. Weiss rule of thumb is not absolutely correct. I mean, there might be some deviation from this 28 by a square of correlation. And it only works if you have enough number of samples. Means that should be larger than, for example, 200, 300, and so on. If you have millions, definitely is okay. But if you have, for example, 50 traces, this rule of thumb doesn't hold necessarily. Let's look at the Hamming weight of the Spock's output that I already calculated. Look at here. This is the result of the attack using the Spock's output with the Hamming weight. And for example, we select this guy and say, here is actually my point. Yeah, you see the correlation as what? 0.53 and 26.6. Then I just write it here, 26.6, and the correlation was 0.533. Yeah. Now, the square root, or other way around, we say n should be equals what? Should be 28 by the 0.533, which is the correlation to the 2. And it says that roughly 100 traces are enough to perform the attack. Yeah, it's 98 point something. Yeah, then it's roughly 100 traces are enough to perform the attack. And if I change this to 100 and using again the Hamming weight of the Spock's output, now we can wait a bit and see what happens. Now with 100, you see still the attack is possible. Yeah? And since we use 100 samples, then we just calculate. Now 0.533 should be somehow the threshold here. I mean, everything is above that, then is somehow considered as the correct key candidate. One thing that we can also do, for 400 traces, we could also check that what should be the minimum value of the correlation and then have a threshold line. What I want to calculate now is the correlation is a square root of 28 by 400, because we use first 400, and you see is 0.26, yeah? And then it means that everything is below 0.26, which is roughly here, you know, is considered as noise. You know, this is the threshold. But as I said, this is not something like the t-test that you have some proofs for that. You know, this is kind of a rule of thumb. I can also plot Spock's input. You remember again what was the threshold? 0.26 somehow with 400 traces, and you see all of them are actually below that. Means that the model that you have selected does not necessarily correlate it to the power values that you have. The number of samples with just 400. And you should look first 28. The square root of 28 by 400, and see what should be the minimum value of the correlation. You know? Just looking at the result of the correlation and say, okay, the correlation is very high, 0.3, that doesn't tell you anything. You should know how many samples you have, because it's a Pearson correlation coefficient and it's estimating the correlation, and the number of samples that you have is actually telling you or defining what should be the minimum value of meaningful correlation. This rule of thumb, 28 by a square of correlation, comes from very simple example, very simple study. You can generate random values, just random values, two random values, completely random, distributed randomly, yeah, and with a different size. One's with 100, another one with 200, and then with 500, and then with 1,000, and then 10,000. And every time correlate them. Means that if they are just random data, they are not related to each other, and then repeat this and get the average of the correlation. Now you will see when you increase the number of samples, the value of correlation also decreases. And this exactly tells you that if even the random values are, these random variables are just random and completely unrelated to each other, what you should expect as a minimum value of the correlation to be meaningful. They should be higher than something to be meaningful. And if you have a low number of the samples, then correlation is anyway high. You know? Then wrong value and wrong model is something, and having not enough samples is something else. Now, the last thing that we discussed today is how to perform CPA with large number of measurements. Because what happens in reality is not something like performing the attack on a device using 400 traces. If the time for this is actually over. If you perform the attack on protected implementation, then you may need actually millions of measurements. Then you need an efficient implementation of the CPA, because what you have seen is always based on a matrix and a vector. Either you need very high amount of memory and then read everything into the RAM and then perform the attack, and then you need also pretty high number of CPUs to handle this, and then you need to have an efficient implementation of the CPA. Because first you have a huge number of measurements sometimes, and also every trace has is very long or has many sample points. For example, if you want to perform an attack using 2 million traces and each trace has just 5 sample points, and if we imagine that everything is well compact and every of these sample points has just 1 byte, 8-bit signed integer, then you need just 10 gigabyte of memory to just read this. What we have seen together were based on MATLAB, and if you just import them in MATLAB, every single value of these measurements will not be a single byte. It will be, for example, 8 bytes. It can be converted to double. Of course, you can ask MATLAB to not convert them to double, but if you want to calculate, for example, or estimate the correlation, they should be first converted to double for every time that you call CoreCoF. Then a lot of memory and then changes from the representation are required. At the moment, most of the laptops have more than 16 gigabytes of the RAM, but you may not have 10 gigabyte free for that. For that, we would love to see something else. Now, this is something that you have seen during the first assignment, which is one past parallel computation of covariance and arbitrary order statistical moments. About this statistical moment, I think I already discussed or explained you something shortly. Based on that work, I explain you how we can do incremental and pairwise computation of these things that we need for correlation. I mean, the idea is something like this. Why we need these incremental formulas? The idea is that, as I said, the traces are very, very long, or you have many traces. And then you cannot read all of them into the memory. The idea is that to, for example, read one trace from the hard disk or a couple of traces from the hard disk into the memory, compute something about the correlation for all key candidates, and then get rid of this from the memory and read the next one, and then update the values for the correlation. Either, as I said, you update the value of the correlation one by one or bunch by bunch. Now we see the incremental and pairwise formula that are required for CPA. First, the mean we need, which is mean or average. By average, we estimate the mean is the first row statistical moment. And the variance is second order centered or central statistical moment. What is the mean? We say mean is 1 over n of all I from 1 to n, and then xi. No? And then variance is 1 over n, sigma again the same way, of all I, xi minus mu square. And this is central or centered statistical moment. Why centered? Because, this guy. Because you bring it to the center. There is a distribution, you remove the mean. When you remove the mean, you bring it to the center. But you can have actually something else. You can have this guy. This is also second order statistical moment, but it's not centered. It's not centered. It's row second or second order row statistical moment. There are the other ones that I do not explain it today. Later, when we deal with the countermeasures, you will see that there are some other statistical moments like third order centered statistical moment, third order standardized statistical moment, and so on. And covariance, and you know already the formula for the covariance. This is what we know. Then here at the top, you need the covariance, to calculate the covariance, and here is again the variance and the variance to calculate the correlation. Now, the mean, I think most of you already know, we discussed about this in the assignment, that you have q n minus 1 elements, and you already calculated mu of q, and then you now get a new x, which is xn, and then having the mu of q, you want to calculate the mu of q prime, and the q prime is the union of q by the xn. Means that you do not have this x1 till xn minus 1 anymore. I mean, you got rid of them, and you only have this guy, and n minus 1 means that you know how many samples you had, and then xn, which is the new value coming to the set. And this is super easy. This is the formula for mu of q prime is the 1 over n, all possible values of xi from 1 to n, and then you say, this is easy. I have only the sigma of n minus 1 plus the new element. And now if it's divided by n minus 1, this is mu of q already. And I can write the formulas easily like this, and finally end up with 1 over n mu of q minus mu of q plus xn. And then if I define delta and say delta is the current mean minus new element, or distance or difference between the current mean and the new element to the set, then I can actually write that here by this way I can update the average or update the mean by saying that mu of q prime is the old mean minus delta by n. Super easy, Now, how about the variance? Similar to before, you don't have this set anymore. N minus 1 element, mu of q you have, variance of q you have, and xn is the new element to the set. What you want to calculate is the variance of the q prime, the new set, which is the union of q and new element. What is important here, we write the variance as actually the S, the sum of Q2 or sum 2 of Q. And then we say if we have this value, at any point we can divide it by n minus 1 and get this variance. Means that the division is easy. You don't need to just do something. Here this is something that you have. Then if we don't have the variance, but we have S of Q2, then it's also okay. And for the Q prime is also the same, 1 over n by S2 of Q prime. Now the formula is a bit more complicated, but you can follow this, that this is the formula of the variance of the Q prime. And then again, you say 1 over till n minus 1, similar to before. There are two parts now, and this part you easily write based on the delta, means that mu of q prime is something that we have seen in the previous slide, that you can write this, the current mean plus delta by n, minus, there was a minus here, but then this minus comes here, it makes this positive, or plus, and xn is exactly this n, and here you write again mu of q prime by this, what we have written here, because delta was the mu q minus the new element. And then you start expanding this part. And if you write it like this, you may write it by yourself and see whether it's correct or not. One part becomes 0, because this is actually the average minus the average. And then here will be the result. Means that we do not deal with the variance, but we deal with the S, which is the sum. Means that I have the old sum plus delta to the 2 by n minus 1 divided by n, and I update the S2 in this way, and anytime I just divide it by n to get the variance. But it means that I have to keep actually this guy instead of the variance. Now, how about pairwise formulas? Not incremental, means that you have two sets, or you read bunch of the traces, you calculate mean, variance, covariance, everything, and then you update the mean and variance and covariance of the attack. Means that you do not update the main result of the attack one by one, but bunch by bunch. Here it means that Q1 has n minus 1 element, Q2 has n and 2 element. Sorry, Q1 has n1 element and Q2 has n2 elements, and each of them has the mu and also the sum or variance. And then the new set is the union of both sets, and these elements we already got rid of them. We don't have them in the memory. What we have only, now we want to have the union of them and get the mean of q prime and the variance of the q prime. Now we define delta. Delta 2 and 1 is the difference or distance between their mean. And then mean is easy. Select one of them, mu of q1, and then plus n2, the cardinality of the second set, multiplied by delta by n, and now variance is again, as I said, is dealing only with S, and the sum of both S's plus n1 multiplied by n2 by delta to the 2 by divided by n. If you want to know how, either read that paper that was a couple of slides before, or you can sit down and write the formula by yourself. It's easy. Yeah, I mean, it's trivial because it's now solved. Yeah, but it's not something which is hard to do. Yeah? As I said, any point in time, then you have to divide this by n to get the variance. This was about mean and the variance. Now how about the covariance? The incremental formula means that you have now two elements in your set. Yeah? I mean, every element is a pair, but you have n minus 1 elements. Now you have the mu of only x, you have the mu of the only y, and you have here again new element or new pair which comes there, and then you have the covariance already, and you want to now have the updated covariance. But keeping again in mind that we do not update the correlation directly, we update the covariance, and every point in time again, we normalize the covariance to report the correlation. Now again, the union, this is also important that for the covariance, similar to variance, we have the S, yeah, not the covariance by itself. And now you know how to update the means. Yeah, this is already what you have learned. And now this S2, this guy, which is the covariance or related to covariance, is updated only like this by n minus 1 by n delta x by delta y. I mean, you already know delta x and delta y, which was in the same delta as before, means that the current mean minus the new value. New value is, for example, x here, and the new value for y. These are also written here. And for the pairwise formulas, I mean, then you have two sets, and then you want to now update the covariance like this. I will explain why we need this and how we can use this. But if you want to have more information about these things, there is a paper that I have co-authored 8 years ago about robust and one-process parallel computation of correlation-based attacks at arbitrary order. The link is there if you are interested. First of all, about these incremental formulas. Somebody may say it's actually not required, no? Particularly for the variance. Variance is the expected value of x minus mu to the 2. No? Somebody may say this is what? This is the expected value of x2 minus 2 x mu plus mu2, right? And say the expected value of x2 minus 2 mu of expected value of x plus, actually the expected value of mu2 is mu2. No? And what is this? Is again mu. It will be expected value of x2 minus what? This is 2 mu2 becomes minus mu2. No? Or you can write it as this, yeah? Expected value of x2 minus expected value of x to the 2. Somebody may say, why do you actually calculate this incremental formulas? You can easily calculate it like this. Because this one you can easily update. You can also, this one, update it easily. The problem is numeric instability. Means that this becomes a large value because it's x to the 2. And this becomes also a large value. A large value minus a large value in a floating point domain, then you lose accuracy. And at some point, you cannot estimate this variance correctly, and you lose the accuracy. If you remember the name of the paper, which I showed or said a couple of slides before, was robust and one-pass formulas. Why is one-pass formula? Because if you look at this formula, you need to first pass all data to get the mu. And again, one more time, pass all the data to get the variance if you go to a normal way. But for power analysis, it's not possible. It means that you first process everything till end to get the mean, and then again process everything from a start till end to get the variance. If you process 1 million traces, you cannot report the correlation because you calculated mean based on 10 million traces, for example. Yeah, something like this. And this should be one pass, means that you process data only once, and it's robust. Why is robust? Because it doesn't have the numerical instability. We look at the variance formulas together. It's not a large value. It's just multiplied by n. It's already centered. Do you remember the formula for S? Yeah? This is already centered. This is the formula for that. When it's already centered, of course it's a squared, but it's already centered. Means that by having many more measurements or samples, then it scales still linearly. Yeah? And then you don't get into that trouble of instability. After knowing why we have these formulas, then how do we use them in the attacks? You remember we said we have n equals 2 million traces. Yeah? And let's say large T is the number of sample points is 5,000. Yeah. Then here is traces, and here number of sample points. And then let's say K is 256 as the number of key candidates. When you want to perform the attack, suppose that we have the incremental formula, not the pairwise formulas. When you want to calculate the correlation, or let's say correlation like this, between what? Between x and y, and x I call this power values, and y hypothetical power values. No? Hypothetical power. Now, if you again remember, we had a matrix as a result of this correlation. The matrix has the size of the K, number of key candidates, and the size of the T, the number of points that you have. Now, for X, which is completely independent of the key candidate, it's the power values. They are not dependent on the key candidates. What you need to have to calculate the correlation, you need the mean, and you need also the variance. Then you have, let's say, mu of X of the size. I just write the size here. What is the size of the mu? Because it's completely independent of the K, it's actually 1 till T. For every sample point, you need a mean. You also need a variance, or this S2 of X is also 1 till T, completely independent of the key candidates. And now for the hypothetical power values, Y. You need mean, and you need also the variance, means that mu of Y of the size of 1 till K, and S2 of Y 1 till k. Means that they are completely independent of the sample points, but depends on the key candidates. It means that now you have a vector of t elements for the mu of x, a vector of 1 till t elements for the variance of x, and a vector of k size of, or vector of a size of the k for the mu of y and for the variance of y. That was only about mean and the variances, but you need also the covariance, this C2, you remember in the slots incremental formulas, C2 or the covariance. I think it's written somehow like this, or let's say for the covariance, which we had actually S2 and Q, this is what we have called it. This depends on the number of key candidates and also number of sample points. Means that this is of the size of 1 till t and 1 till k, which is exactly this matrix. Means that the memory that you need is that the size of the t by k, of course double, the highest precision that you have, and two vectors of the size of the k for the mean and the variance for y, and the two vectors of size of the t for the real values, for the mu and the variance. That's all the memory that you need. You read a trace, you read a trace, it has a plain text, and based on the key candidate, you update actually these guys. For all key candidates, because it has a plain text, and you put the plain text all key candidates and you update this. Because you read this, that trace, what you do, you update also here. Now all sample points individually. And for all of the key candidates and all of the sample points, you update also the S2 of Q, incremental formula. Then you have this. At any point in time, for example, after 1 million traces, after 100,000 traces, any point in time, you divide this matrix by the number of samples that you have. You get the covariance, because this is the sum. You get the covariance. Then you divide it by the square root of this guy and this guy. Of course, you don't have them. You have there also S. Then you divide by them, normalize them, and you directly have the correlation. And then you report the correlation, because sometimes it's like this. You don't know how many traces are required. You start measuring, and the oscilloscope is measuring and collecting data, saving to the file. And now the machine server reads this file at the same time automatically and say, hi, there is a new file, and then update all of this. And for example, you set it in a way that, okay, after every million traces, then report also the correlation. Then the server or machine that reads the traces also updates and saves the correlation results into the file, and then you watch after, for example, 10 million traces, you don't need to continue, because you see, I have the result already. No, it should not be like this, that I always measure, for example, 100 million traces, and then I run the attack and do I need more traces or not? I don't need more traces. Then this way you can, in an online way, always have the result and check whether you need to get more traces or not.